Okay, so thank you so much for the invitation. First of all, I'd like to thank the organizers. It's an extreme pleasure to be back to Trieste and also to ICTP. And well, today I'm going to talk about integral models, integrability, versus the some kind of field theory, but gauge theory. And of course, there are various different differences. In fact, there are so many differences in the literature about. Oh, okay, I have to turn. Oh, I see. Yes.
Need to find a suitable boost. Yes. And then turn it on. Right. Okay, it's better. Yeah. Hopefully, you can hear. So, so there is a relation between integrability and gauge series, and there are various proposals in the literature. But quite often people use the integrability to try to solve the gauge theory. It's something like there is a gauge theory, it complicates things, but maybe you specialize to some particular sector, or you take some special gauge theory, topological gauge theory, etc. And then there is some integrable structure there, so you try to take advantage of that to solve the gauge theory, for example. So that's roughly in this direction, trying to use the integrability to solve gauge theory, which is a very interesting thing. Except that mostly what I'm going to talk about is the opposite direction. So namely, I'm going to use the gauge theory or quantum field theory as a tool to understand whatever is known about various integral models in the literature. So that's the direction I want to go. And well, let's see. So then what aspect of integrable models I want to understand? Well, today I would say that I want to understand minimally the Yang-Baxter equation, which I call YBE, with the spectral parameter. Right, so this is what I want to understand. Well, there are other ingredients, but I think it's often the case that this Yang-Baxter equation is the definition of integrability, although there are several different definitions of integrable models, but this, I think, is one of the canonical ones, so I want to understand these particular equations. Well, so what I understand means that, well, sometimes you might want to construct new solutions, but also sometimes people find solutions for certain cases, but people hasn't found a solution in some cases. So we want to explain the pattern of what is known about Yang-Baxter equations in the literature. So these are the things I want to do, starting with gauge theory. Now, here I emphasize the fact that I'm going to think about the Yang-Baxter equation with a spectral parameter. And that's important because that's really a crucial part of the story. So it's likely that most people are very familiar with the Yang-Baxter equation itself, but just to remind you what Yang-Baxter equation was. So Yang-Baxter equation, so there is some operator R. So it's endomorphism of some vector space V. So it has, in a sense, it has four indices, say IJKL, for example. IJKL, if you choose a basis of this vector space. Say it's a big vector space, it's going to be in some representation of some group, for example. Say SU2, spin J representation. So this is this vector space V. And then, so this is the operator. And then I consider the three tensor products of vector space V times V times V. And then on this space, I could define the R matrix. Let's see. So I could. So this R itself is endomorphism of V times V. But for example, I could take R12, which is the R acting on the first two, times the identity on the third component, for example. So this is endomorphism V times V times V. And similarly, I could define 1, 3, 2, 3, for example. And the celebrated Yang-Baxter equation says that that we have this equation. Well, it's important, so let's write here so that everybody can see. 1U. Sorry. Okay, I'm going to write this afterwards. And R23 is equal to R23, R13, R12. So this is the identity. So this is the element of the endomorphism. So you can take a product, compose it, and this is the equation. Now, so this is so in some cases people are really interested in this type of equation, but I need a little bit extra ingredient, which is a spectral parameter. Oh, there's a color choke, so I'm tempted to use it. So in my case, what happens is that there is a one parameter family of R matrix. R matrix is a function of parameter, and this is the spectral parameter. I might write it Z, for example, sometimes, or U. And then there is the equation here. Well, in general, actually, it depends on the two parameters. But here imposing a condition that it depends only on the difference. So that's one parameter, if you care about such details. But anyway, for the most typical case, it's just one parameter. Now, then there is a parameter here, U plus B, and B. And then these are U plus B, U, for example. So that's an interesting equation where there's a particular pattern in the argument. And so this is the Yang-Baxter equation with the spectral parameter. And so one interesting question is whether you can find a solution to this. And if you don't know anything about the integral models, the most brute force way I would do, it's just like the order of components of the matrix, for example. Say, for example, if ijk runs over two indices, for example, that has 2 to the fourth power 16. Well, let's see. Anyway, there are many components. So, and then write down the components, and then just write down the equation and try to solve it. That's the most naive thing to do, except that then you immediately realize that it's not easy to find a solution, because this is an over-constrained solution. Well, for example, if this index I, j, k, etc. runs from 1 to n, this gives order n to the 6 powers equations. But R matrix itself, it has only 4 indices, R to the n to the 4th power, for example. So it's highly over-constrained. So it's very hard to find a solution. And if you do a linear algebra, for example, unless there is some miracle and then there is some linear dependency between these equations, you won't find a solution. But that miracle happens, and then that interesting question, why that miracle happens. And the question is to understand that miracle from gauge theory. Well, of course, this is not the only approach. People try to take advantage of symmetry. For example, one approach is to take advantage of symmetry, and people use the quantum groups and other symmetries, which I sometimes come to. But I'm working a few theories. I want to understand hopefully everything in gauge theory language. Now, why is this equation important? Because it's related with the existence of conserved charges, which is another characterization of integral models. So suppose that I have this R matrix. Then I could define a statistical mechanical model. Well, here I define a classical statistical mechanical model defined on the two-dimensional lattice. So there is a two-dimensional plane. And there is a statistical lattice. And well, for example, for the simplest case, let's take the square lattice. And let's also assume that that it's a torus, for example. Periodic boundary conditions. Sorry, this is supposed to be on the boundary, for example. The order rest is supposed to be a lattice, for example. And then you can define a statistical partition function by associating a factor of R to each factor. So what you do is that you associate this spectral parameter. Well, okay, first of all, R depended on a spectral parameter. So you could associate, for example, the same spectral parameter U and let's see. For example, I could associate the same spectral parameter U here, etc. And then once you see this intersection, you associate this R matrix here, which has 4 indices. And then when you connect these 4 variant vertices, you're going to sum over the corresponding indices. So namely, if you have this, for example, IJKL, for example, I would say that there is a Boltzmann weight IJKL, for example. But now suppose that there is PQRS, for example. And then I'm going to also associate PQRS. But when we connect these things together, I'm going to make identification that S equals to J. So this S is replaced by J. So take a product and sum over the J. So each time, so you start everything, you associate the R matrix to each vertex, and you're going to connect everything together. And each time you connect it, you sum over the corresponding index. And by repeating that, you obtain something. So eventually, you contract all the indices, and you define the partition function.
So this is a torus.
Yes, in this case, it's a torus. And if you want, so you can also try to have the boundary condition, like a fixed boundary condition, etc., on the boundary. Well, in those cases, you have to make sure that integrability is preserved on the boundary condition. And there is a reflection, like for example, K matrix. There is a similar equation involving. You have to take into account the effect of boundary, and then there is a boundary generalization of the Yang-Baxter equation, for example. So, so this defines so two-dimensional statistical lattice model. And once you have this statistical mechanical model, so this is just the definition. But what's crucial is here is that this Yang-Baxter equation guarantees that this the commute. Well, let's see. Should I explain this? Okay. Well, maybe I just state the fact. So from here, so this is the full partition function. But for example, you can, instead of computing everything at vertex, you can try to first compute this part, and then and then combine everything together to form the whole two-dimensional lattice. So namely, you might want to first compute this thing, namely single layer, where because of periodic boundary condition, it's identified. So this is a transfer matrix. And then suppose that there's a spectral parameter here. So this is known as a transfer matrix. And the partition function, and then the power of this thing, where this L is the length in this direction. And the crucial point is the Yang-Baxter equation means that these two transfer matrices commute. Two transfer matrices with different spectral parameters commute, and hence you can expand Tu in U to, and because everything commutes for arbitrary values U and V, you can expand, and the coefficients should also mutually commute. So if you expand, like Tn Un, for example, then they should mutually commute. So that's another characterization of integrable models, that they are mutually commuting charges. So for this reason, well, what's crucial is that you need a spectral parameter U to do this expansion. If you have a solution of the Yang-Baxter equation without this U, you do not necessarily have this conclusion because you simply cannot expand in U. Right. So this is the well-known stuff in the integrable models. But the reason I spend some time explaining this is it's actually, although there are a lot of literature about trying to use gauge theory to understand some aspect of integral models, there has been a long-standing question of how to understand spectral parameter in gauge theory. And well, I'm going to explain a little bit more later. But before coming to details, well, first of all, we have a Yang-Baxter equation with a spectral parameter. And then there are several different approaches to this. And I have tried several different things over the past 5 years or so. And what I'm going to talk about today is one approach which uses four-dimensional gauge theory. Well, so this is somewhat like a Chern-Simons-like theory, but in 4 dimensions. And this approach has been, first proposed by Costello in, I think, 13. It is a very interesting paper. And so we are trying to take advantage of the full power of his understanding. And so there's what I'm going to talk about is based mostly in work in progress with Kevin Costello and Robert Digraph. Digraph and Ed Whitten. So that's what I'm going to talk about. And well, before talking about that, let's also mention that there are several other things I have tried. Another approach to this. In fact, that's what I talked about here in exactly the same room 3 years ago. In fact, but I know that there isn't too much overlap, so I'm not going to assume anything. And also, I'm now writing a review about this whole stuff, which is supposed to be very pedagogical. So if you're interested, please have a look once it comes out. But anyway, so the another approach is here. I'm going to use the four-dimensional, well, not necessarily four-dimensional. The other idea is to use supersymmetric quiver gauge theory. And this approach I call the gauge YBE because it's a relation between Yang-Baxter equation and gauge theory. And well, I intentionally wrote the Suji gauge theory somewhat vaguely because there are actually several different versions you can do with this. The original story I worked on was 4D n equal 1, for example. But you can also go to 3D and then 2D, for example. 2, 2, for example. And right, so that's, and then, well, what's interesting about this story is that well, first of all, the main idea here is that there's a Yang-Baxter equation. So what is the counterpart of that here? Well, the simple answer is that it corresponds to some duality, which I call the Yang-Baxter duality. So it's a duality among quantum field series, quiver gauge series. So Yang-Baxter equation is promoted to duality. But this is very nice because once you promote it to duality, you can compute various different partition functions, for example. And then you can obtain various different answers, for example. It's just that one answer, but sometimes, for example, in the typical case I worked on is that originally I started working on S1 times S3, but there are also supersymmetric localized partition function, which is some time ago I computed with Francesco and also Tatsuma Nishioka. So I also computed these observables, and then we obtained different solutions of Yang-Baxter equation. So it's actually, you could obtain new solutions. And the new solution is it's supposed to contain all the known solutions of the star triangle relation with the positive Boltzmann weight. And it's a crazy generalization of the Ising model with many parameters, continuous spins, discrete spins, etc. And it involves, for example, well, function-wise, this involves some special function known as the elliptic gamma function. And well, you can take various degeneration limits. There is a quantum dialog, a Poch Hammer symbol. There you can go to gamma functions. Well, the gamma function case is a little bit subtle, but okay. Yeah, sure. There is an expression involving gamma functions, theta functions. So there are various special functions appear. And so there is a very nice structure here. Well, so I'm very fascinated by the story, except that by talking with people, I realized that this is not necessarily the type of the integral models which people mostly encounter. So namely, these are solutions typically are not quasi-classical. So what does quasi-classical means? Well, quasi-classical means that there is some parameter, expansion parameter, like h bar for this R matrix. So if you have this R matrix RU, for example, but suppose it has expansion parameter h bar. And then suppose that it starts its identity, and first order, let's write it small r plus order h bar squared. So in some cases, there is a nice expansion parameter around which you start with the identity and then expand to the first order and the second order, etc. And if there is such a parameter, the solution is called the quasi-classical, for example. Well, but many of the solutions are not quasi-classical, whereas many people in the literature encounter quasi-classical solutions. So I'm not completely reproducing many of the things most standard stuff people are discussing. Now, here in this approach, I'm going to, these are particularly useful for seeing can see quasi-classical solutions. Solution. And in fact, it's useful to see the classification of the quasi-classical solutions, as we will see. Or maybe I'm going too slow. Yeah, okay.
Sorry,
yes.
Very naive question.
Yes.
So in the second approach, so even if we have the same n equal 1 supersymmetric derivatives,
yes.
Changing for manifold S1 cross
yes.
S3 or S1 cross S3 over gamma.
Yes.
So the integral model will be changed.
Right.
So do you have any idea why this kind of thing?
Well, any idea why? Well, from the viewpoint of integrable models, for example. I mean, from the viewpoint of integral models, it's very hard to see that because it looks like a completely different integral models. And unless you know the underlying gauge theory, it's very hard to see. Well, except that there might be a different answer of the different type, which is like maybe there's an underlying geometrical structure, algebraic structure like a quantum group. It might be the same, for example. For example, these are associated, as you know, with the Skryning algebra, for example. And well, I don't really know this S3 mod gamma case, but given a Skryning algebra, you can try to change the representations, for example. So maybe it might be that changing the representation might correspond to changing the geometry. Or maybe we are identifying the even new structure, for example. For each form there might be new algebraic structure, for example. That would be more fascinating, but I don't necessarily know because, I definitely to see that the quantum group or elliptic group type structure here, but not necessarily directly so far in this approach.
I think it leads to generalization of the elliptic.
Yeah.
When you include CR.
Yeah. You're right. Well, so you're talking about the one by Odesky, for example, Pagin Odesky. Well, sorry, but Felder doesn't necessarily have this R, for example.
Yeah, so that's
right.
why I'm saying.
Yeah. I think so. So I don't know, but I do suspect that this might be a new algebraic structure underlying behind that. So if you know, so this at least can be defined for SLN, and it has two deformation parameters. So these are continuous parameters, like a Q of the quantum group, plus integer, R, for example. Yes, so that's a discrete parameter. And maybe it might be a completely new algebraic structure. That would be very fascinating. And to some extent, we already know the R metrics. And in some simple cases, given the R metric, you can define algebra easily. But that's R metrics, a complicated R metrics, whose indices are continuous parameters, for example. So standard method doesn't necessarily work. So, but anyway, I think there is a lot to understand, even mathematically, about, because these are concrete solutions. It goes through quantum field theory, but the resulting solution is very concrete. And well, at least I should say what the spectral parameter is. So in this approach, spectral parameter becomes, in this approach, as we will see, a position, well, geometrical position on surface, which I write C. And here, in this case, it's actually related with some U1R symmetry in supersymmetric gauge theory. And so namely, there is a U1R symmetry in the IR could mix with the Flavor symmetries. So there is mixing, and there is a parameter space, and that type of things, yeah, is related with the spectral. Well, in fact, sorry, the U1R symmetry and the IR, I should have said, right, is related with the spectral parameter. And well, so there are some questions about how to relate this, and I have some thoughts, but I won't say anything today, at least. And well, of course, U1R symmetry typically in the brane realization is a rotation in the transverse direction. So that's also geometrical, so there might be relations. And in fact, since I started saying this, there is another thing I tried, which I might like A, because it's a slightly different category. So another approach is to try to use the scattering amplitude. Of planar scattering amplitude. of 4D n equal 4 and 3D ABGM theory, n equal 6 ABGM theory. So in this type of approach, whenever there is a, for example, well, that's exactly the case in ABGM, where there is a line, I really regard it as a crossing of particles, for example, gluons. And then there's some interesting spectral parameter. There is a nice structure. And in particular, the R matrix, the one consequence from this is that R matrix has written it as an integral, as Grassmannian integral. Because people are trying to write this scattering amplitude in terms of the Grassmannians. So interestingly, some of the R matrices for Yangian for PSU22/4, OSP 2,2/6, so 6/2,2 has nice Grassmannian formula, for example. Although in this case, unfortunately, the minimal spectral parameter is like deforming the helicity, and the physical meaning isn't completely clear. So let's try to describe this theory, Costello's theory. And Costello goes through a series chain of arguments, starting with 4D n equal 1 supermills, and then do the twist, giving a master fermions. Except that after all, the resulting thing, what is crucial is very simple. And well, let's consider 4 dimensions. Well, first let's write down the action, and then try to explain. And then this is a sigma times c. And then there is a dz, which Chern-Simons A. So this is a very simple action. So let me explain the notation. So first of all, what's crucial is that 4D geometry is always of the form Riemann surface times Riemann surface. So this is where the spectral curve lives. So I said the geometrical surface, but this actually is C. The C I wrote over there. So this is where the spectral parameter lives. And this is another surface, which I could take, for example, for T2, for example. So this is the surface where integral lattice model lives. And let's take the coordinates to be x, y for the first sigma. And then there is a complex parameter, which I was writing z here. So this is a complex parameter. So say, let's write the real part and imaginary part as t minus t and theta, for example. I will not use that often, but z and z bar. So in particular, I have assumed that this is a complex manifold. So there's a complex structure here. And well, it actually turns out that the theory is topological. So we need a holomorphic structure here on this Riemann surface. In fact, already here, I already needed that. And here, the theory is topological along this surface. I didn't use any metric here, like for writing down this action. Now, this itself is already actually very interesting because typically in Chern-Simons theory, you wanted to the Chern-Simons theory. Say, let's start with the 3D Chern-Simons theory, what people are more familiar with. And in that case, you wanted to define a 3D Chern-Simons theory on arbitrary 3 manifold. And that was actually crucial for understanding knot invariant because there is a 3D covariance. So the original motivation of Witten was that there is a Jones polynomial, but that's defined by projections. And somehow knot theorists could see that it's independent of the way its projection is done, but that becomes completely trivial in Chern-Simons formulation. And that was the power of the 3D covariance. So that's very crucial for application to knot theory. Here, I'm using a different thing. So I don't necessarily have the covariance is 3 manifold or 4 manifold in this case. And I just restricted the geometry to this case. In fact, that's a little bit of a trick. which by hindsight is very simple, but so you need to change your mindset a little bit in order to discuss integral models with our Yamazaki equation with the spectral parameter, so that as compared with discussion of knot invariance. Right, and then so what's this A? Well, A is what's also there is funny is that this A is a connection, of course, but we actually don't use the some of the components of this connection. AZ bar, DZ bar. So no AZ. Well, no AZ doesn't mean that we are fixing the gauge so that AZ equal to 0. That will break the gauge symmetry. But a lot of what I'm doing is that the value of AZ is unspecified, and I'm not really using that to write down this action. Now, the Chern-Simons A is the standard Chern-Simons term action. Chern-Simons action, AHDA plus cubic term. So if you like, you can integrate the parts. And I think there is a factor 2, I guess, like Z, FHA, for example. FHF, sorry. So this is by integrating parts. So this is like a theta angle, but the theta angle depends on the complex parameter Z. And also, for example, the parameter here, H bar, 1 over H bar, low to H bar. So this H bar obviously plays a role of the Planck constant, but it's not necessarily quantized. So in the 3D Chern-Simons theory, it was quantized. That was a level. And that was because, well, one way to explain that was, in fact, we did similar operation like this. So in that case, there's a Chern-Simons term defined on the 3 manifold. But for that, you need a trivialization of the gauge field, which doesn't necessarily exist. So you do integral parts. You can do the integral parts if the 3 manifold is the boundary of the 4 manifold, and to write it in the boundary of 4 manifold, but it depends on the choice of the 4 manifolds. So that's why this level was quantized. But here, all the fields are already defined on the 4 manifold. So that's this Lagrangian. Is there anything else I should explain? Right, DZ, Chern-Simons. Right, so I'm going to consider a slightly generalized version of this momentarily. But this is the simplest case. So it's extremely simple action. Now the question is, what does it help? Well, just like ordinary Chern-Simons theory, we attempted to compute observables. And the good observable is the Wilson line. So in the case of the compact group, usual Chern-Simons theory, the Wilson line gives like knot invariance, so we attempted to do similar things. But first of all, we have this product geometry, so we have to think about which direction the Wilson line spreads. Now, we have to be careful with the fact that there isn't really AZ. So in the usual way to define the Wilson line, you have to do the parallel transport using the gauge connection to compute the holonomy and then take a trace. However, there isn't really no AZ. So you cannot really transport in the direction of Z. So what you want to do, at least I'm going to do, is to consider Wilson line here on this plane. And let's take this to be T2, for example, elliptic curve. So remember, this is supposed to be where the lattice model lives. So depending on what kind of boundary conditions you want for the statistical mechanical model, you might have to think about different surfaces. Say it might be a disk if you want the boundary condition. Then you have to think about the boundary conditions of this. But let's say you have a torus, for example, so that the resulting statistical mechanical model has periodic boundary conditions. And let's do the similar. Well, and then what I want is exactly the same picture, which I wrote 10, 20 minutes ago. Which was this picture. Right. But now, the meanings are slightly different. Well, first of all, maybe I should orient these. So these are the Wilson lines. So each of these becomes the Wilson lines. So this is a sigma, which is a topology, which is along which the theory is topological. So I might call it topological plane. Now there was a parameter. Well, let's see. First of all, if it's a line, then it should be at a particular point on this surface. So the whole geometry is this times the surface, C. Well, the curve C, except that in this particular case, this surface C is taken to be a complex plane, as this Z. Z is a complex coordinate, for example. Well, I'm going to comment on the generalizations momentarily, but this is the simplest case. So there is an infinity. And then it has a fixed point. So for example, this used to have a spectral parameter, for example. Let's see, parameters like Z. Let's say W, for example. And these are located at point Z and W. Well, you can try to change the positions, in fact, if you like. But these are located at different positions. So the idea is pretty simple. So there was an unknown parameter, but that was turned into the coordinate of the extra dimensions, if you like. And this Z and W should play the role of the spectral parameter. Well, except that there could be various objections to this. So, well, okay, so at least the statement one might want is that I consider the expectation value of these Wilson lines representing the statistical lattice, and then compute the expectation value. And then that reproduces the statistical partition function of the integrable models. That's the type of things. But there are many things. Well, first of all, why it's integrable. But even before coming to that, it's not even clear why this is the statistical mechanical model in the sense I explained. So namely, in general, well, in the statistical mechanical model I mentioned, everything comes from the local interaction at the vertex. So namely, there isn't a long-range interaction between the variables here and between the variable there. So, so you have to make sure that whatever you're computing here, after I factorize it into local contribution from here. Once you know that, it becomes closer to the statistical mechanical model I was talking about. Now, let's see. Now there's one peculiar, yet another peculiar feature of this theory, which is that this theory, so which I tend to call Costello's theory, very interesting. This is power counting unrenormalizable. Well, because if you don't have this in 3 dimensions, that was the usual Chern-Simons term, but you have this extra coordinate dz. So, well, it depends on how you normalize this. But if you keep the canonical dimension for the gauge field, there is a dimension full parameter here, which makes the theory power counting non-renormalizable, which looks bizarre. However, well, this is a nice theory, and in particular, due to the equation of motion, all the counter terms which you can think of, gauge invariant counter terms actually vanish because the equation of motion is like basically f equals to 0. So, so it actually doesn't make too much trouble that the theory is not power counting unrenormalizable. And Kevin Costello has an amazing story of trying to use the Battelin-Velikovsky formalism to define nearly mathematical rigorously perturbative quantum field theory. And he has shown that this theory is is finite, except that please don't ask me why, because some of the arguments I still don't understand. Yeah, but anyway, you can already see that the usual problem associated with the counter term, it's not there. And also, well, if you're really skeptic about this, for example, there's actually a realization of this starting for four-dimensional n equal 1 super MELs, and then try to give a twist theory, giving a master fermions, etc., and that will give a UV completion to this theory. So if you like, I could rely on that, and that itself is fine. Okay, but anyway, the reason I said that this bound quantic only normalizable is that the theory becomes IR free. So long distance physics is trivial. So suppose that I have this complicated set of Wilson lines, and then try to do the perturbation following the usual rules of quantum field theory. And what I do is that, well, there are gluons here, and gluons here, and gluons here, etc. I have to think about all sorts of gluon exchange. And then there might be loop diagrams, etc., which you have to think about. Well, except that the fact that the theory is trivial in the long distance means that you really don't have to think about the gluon exchange from here to there, which is far away. So this means that the non-trivial effect should come from the local intersection between these two Wilson lines, right? So here on this surface, it really crosses. So there is a gluon exchange. And if you go to higher loop order, there are more complicated loop diagrams, etc. That will more complicated story. But still, the fact that there is a local contribution associated to this vertex is fine. So that explains why this partition function, which in principle everything is grouped together, entangled together in a very complicated manner, factorizes into local contributions from this vertex. So this is a very interesting explanation. In fact, in the other story of the supersymmetric gauge theory I talked about, similar localization come from supersymmetric localization, bosons of fermions, cancellations, etc. So one loop exact. So that's the explanation there, but here we have a different explanation. Sorry, that's a comment. Maybe I shouldn't. So, well, now once you have this thing, then you can try to compute it. Simply just do the loop computation, one loop, tree-level one loop to loop, to compute the R matrix. And then, well, recall that these are located at points Z and W, so that should give the R matrix. And it turns out this only depends on the difference. Well, which is not too surprising here, because there is a translation symmetry. So in this case, it depends only on the difference. So if you do the loop computation, that should give this one. Well, but it's still a hard problem, as we know in quantum field theories, because loop computation is hard. So the first thing we should do is to try the simplest, namely to do the tree level. So which is this diagram. So what is the tree level answer? So at tree level, so it's the first leading order in H bar expansion. So namely, if you have this R, H bar of Z minus W, but then I might write as identity plus H bar R Z minus W. And what is this?
Well, what is the suppose the case here which computes this R, but if the value is the value of the product of two lines, so what is the result? What is the case invariant observable that computes R?
Oh, R itself.
Yeah.
Yeah, so that's going to be the correlator of two Wilson lines. Okay. Yes, at an angle here, yes. Right, so namely, so the point is that here, there are a lot of different observables, and they might interact with each other, but we can forget about the interactions among them, just concentrate on the, so it's a sort of a factorization of the correlation function of the Wilson lines. Yes. So what is this going to be? Well, you still have to do the integral. You write down the propagator and then do the integral. So there is a gluon, and there are positions here and there, you have to integrate over all the possible positions. Well, except that, but you don't know, well, but here let me explain the slightly different way. So namely, if you have this structure, or maybe do I want here, let's see, ij. Okay, either is fine. But let's see, okay, well, it should be fine. Yeah, so sure, for example. So let's try to compute this. And suppose that there is an index ij, ijkl, for example. And we knew the law from the Farm diagram, which is that whenever there is a vertex, there should be a structure constant. So, so if I double this dummy index by a, for example, then what you should have is that there is a structure constant ij, ika. Well, maybe I should write it here so that the correspondence is super clear. And then here I have a, well, already say anti-symmetrize everything, for example. Things like this. So the answer, at least, without doing much complicated computations, well, the whole computation not complicated, but
So again, sorry to bother you again.
yes.
But, so we didn't say what was the gauge group of the gauge group.
Oh, sorry. Yeah, okay. I didn't say explicitly, but let's take a gauge group G. Right. And in fact, the point is that it's general. Yes.
Yeah, but for example, now L and K are indices in the fundamental representation of this gauge.
Oh, yes, that's right.
A is an index in the general representation of the gauge group.
Yeah. Well. Okay. Sorry. Sorry. Yeah. Okay. So maybe I shouldn't use the notation A or anything like that. Okay.
Because A
Yeah.
usually is an adjoint index.
Yeah. That's right. That's right.
And then, this looks like it's an...
Yeah. Okay. Right. So these are in some representation. So this is in representation R and representation R prime, for example. There could be different representation, for example.
And A is the adjoint, right?
Yes, A is the adjoint, right. Right. And then what you obtain is that, so this R, thank you for asking. I didn't, in fact, say explicitly. Yes. So you can easily see that this should take the form of ZA, TA, for example, TA prime, IJ, for example. IJ, let's see. In this, sorry, IK, I guess. JL, for example. Where TAs are the representatives for the generators. So A is the adjoint index, and IJ, etc., are the indices of representation. Well, this could be the same representation, but I illustrated a general expression, where the two representations are different. So there should be such group theory factor. And then it turns out that this is supplemented by a very simple factor Z minus W. Well, at least it's okay with dimension-wise. As I said earlier, because the theory is unrenormalizable, this theory H bar has a dimension length. So at least it cancels the dimension, I think. And so this is a very simple answer. So in fact, it turns out the answer is exactly this. Well, that requires computation, but it's very easy. Now, it turns out this is the argument. This is what we call the rational solution. Well, so here, see, here the construction, it looks by construction, well, the actual subtlety is which I'm coming to, but by construction, because we could do the perturbative expansion H bar, so the R matrix is quasi-classical. And this expansion R is this classical R matrix, what's called the classical R matrix. And in particular, this classical R matrix satisfies some equation. Well, of course, there's a full quantum Yang-Baxter equation. So if you expand if you expand this way, and then take the term over H squared, there will be a relation. And the relation is that R12 U and R3 V okay, maybe to save time, let's type the sum u plus b plus r2 1 3 r1 2 3. So this is the Yang-Baxter equation, but h bar limit of Yang-Baxter equation, known as the classical Yang-Baxter equation. And people have found the simplest solution of this classical Yang-Baxter equation is this one. So we have reproduced this classical R matrix. Now, there is a very interesting mathematical. So this is about the classical R matrix, but there is a very interesting mathematical result due to Drinfeld, saying that if you know the position, basically if you know this classical R matrix, then by using the Yang-Baxter equation, you actually know. So namely, suppose that you have two classical R matrices. Suppose that I have two quantum R matrices here, satisfying the Yang-Baxter equation, and let's do the expansion and then obtain two classical R matrices. But suppose that we find that the two classical R matrices are the same, and then it turns out that the full quantum R matrix is actually the same. So so this reproduces the classical R matrix, but if we could resort to his general statement, we actually know about the full quantum R matrix, which is interesting as a statement in perturbative quantum field theory, because otherwise you have to do perturbation order by order. But if you take advantage of this structure, the full structure, full perturbative series can be computed from the full R matrix, which is computed by universal R matrix.
But Drinfeld's result says up to gauge.
Yeah, that's right, yes.
Can you have non-totality with this?
Sorry?
Can you have non-totality corrections?
Well, non-perturbative corrections. I see. Well, Yeah. Right. Yeah. At least it's a. Yeah. Right. So it's a finite series. Right. Right. Yeah. I don't think there are any instantones and things like that. So. Yeah. But I don't think there are instantones, etc. And right. So I think so. So that's a physical argument. But I believe that if you look into the argument of Drinfeld, probably it might be somewhere there implicitly. But that I'm not so sure. Maybe some people in the audience might know. Sorry. Yeah. Right. Yeah. So this is well. So at least we have already derived this simplest classical R matrix. This was essentially there already. This was there already in the Costello's paper from 2013. But here we are using a more elementary approach, which is easier to understand for quantum field theories, I think.
So you have another proof of Drinfeld's theorem, or?
No. Okay. That I don't know. Right. Yeah. So that requires the understanding the full perturbative series, right? So perturbative corrections to these, for example, and that seems hard, in fact, right?
Other closed formula for the full quantum R matrix?
Yeah, I think so, right.
So in principle, there is a prediction for...
Yeah, there is a prediction for perturb. So I think at least you can go, we are just lazy, but you can go to while loop, one loop, two loop, etc., and then it should match, for example. That's a very, that's very convincing check. Perhaps I should do at least one loop, for example. Right. Maybe find a graduate student to do the two loop or something. Anyways, I'm joking. But sorry? Yes? Well, yeah, it should be at least order by order. Order by order. Yeah. That's right. Yes. And right. Well, sorry, but in fact, right. So sorry, but maybe I should say that I realized that I haven't told you the most crucial part, which is that. Well, okay. So we already explained the integral of the R matrix, but why is the theory? Why do we obtain the solution to Yang-Baxter equation? Sorry, I haven't said that. which is the very most important part. Sorry, I almost forgot that. That's the problem of doing the blackboard talk. I forget what I'm supposed to talk about. Right. So what is the, well, so Yamazaki equation graphically means that, that there are 3 different lines, for example. And I could change the relative position like this, for example. And usually, well, you have to go through discontinuities coming from here to there, because it's a 2-dimensional picture, and obviously there is a point where everything, there is a 3-point intersection, which is singular. However, but first of all, here we have the spectral parameters, ZW and ZW, for example, and ZW. So although in this plane, this topological plane, it looks like that they are on the, well, they might, when we change it, for example, there is a triple intersection, but actually on this plane, on the other plane, holomorphic plane, where the spectral parameter lives, well, first of all, they are at the different points. So even when it looks like that everything coming together and everything is singular, first of all, they are still far away in the extra-dimensional direction. And besides, well, the theory here in this along this direction is topological. So this is was the topological plane. So it actually shouldn't matter exactly how these lines are written. So the topological invariance, the theory is the topological on this plane, together with the fact that they are separated in the complex plane. Sorry, the C, the curve for the spectral parameter. So these 2 facts explain why. If you compute these two Wilson lines, they have the same explication value. And then this was the Yamazaki equation. So this is somewhat similar to the argument in knot theory. So namely, in the case of knot theory, there are 3 lines, and you change the relative position. That's Leibniz 3. And the usual argument is that there is 3D covariance, and the theory is topological, so you can change the position without changing anything, and that was here. But here, you don't have a 3D covariance, but we have the topological, still have the topological invariance on the 2 plane, and the cost we pay is that we don't distinguish between overcrossing and undercrossing, for example. So in knot theory, we worry about whether it is overcrossing, undercrossing. That changes the knot, which is very crucial. But here it's a plane, so I don't have any distinction. So I lose some information of the knot, but as a compensation, I obtain the spectral parameter. So there is some intersection between the Young's integral model with the spectral parameter and the knot theory. Oh, yes, the time is almost over, right? But yes, but let me just mention. Well, so far I only reproduced this, so maybe some people might be disappointed. But let me spend 2 minutes maybe explaining what the general result is. Well, in fact, we believe that this framework is very general. We can change very groups, etc. Representation. So hopefully we could reproduce quite a bit of the aspects of the integral models. And at least one result, for example, I can tell you in the 2 minutes, I guess, is that there is a classification of integral classical R matrix. R classification due to Belavin and Greenfeld. And well, the precise theorem is a little bit more complicated, but roughly speaking, the statement is that classical R matrix comes with 3 types: rational, trigonometric, and elliptic. What this means is that in practice, R matrix is in some polynomial in Z, or Z and X, for example. Yeah, but there's a polynomial or trigonometric, sine and cosine. And here in this elliptic case, we have theta functions, for example. The R matrix is written in terms of these functions, for example. And correspondingly, the spectral parameter lives on C star, lived on the elliptic curve. Now, there's a counterpart of this. Now, I think I only have 1 minute, but I could tell you in 1 minute, which is that we could generalize the story a little bit. Well, okay, so far I was writing DZ, with Chern-Simons A, but in fact, that implicitly assumed that that was C, for example. Complex plane. The sigma was a complex plane, and that was why I was writing ZZ with a differential Z. C is the holomorphic coordinate, right?
That's what you meant to be a
Oh, sorry. Yeah, I was saying the wrong thing, right? So this was used to be C. Sorry. Yes, thank you. But I could take C to be a different manifold. For example, I could take it to be C star or elliptic curve, for example. And then I take some differential. For example, in this case, there is a simple differential dz. In the C star case, there is a simple differential dz over z. And in this case, there is a differential dz, where these are obvious canonical coordinates here. And I use this in the definition of the action. Well, so this is the one differential. But, well, of course, then you can say that why don't you take a higher genus Riemann surface, etc. Well, now the point is that this is not the complete classification of general R matrix, but classical R matrix. So namely, this is a situation for, sorry, maybe I'm going over 1 minute, sorry, already, sorry, but let me finish in 1 minute. So this is a situation where you can take a classical limit. So h bar goes to 0 is applicable. So here, I have h bar. So namely, this is a parameter, so I could always take h bar to 0 and discuss classical limit. However, the subtlety is that there might be zeros, for example, of W, for example, or omega here. If there's a 0 of omega, it's like sending h bar to infinity. So the semi-classical argument here doesn't apply. So it's an intrinsically quantum theory, at least near that point. And it might be fine as a quantum theory, but it doesn't necessarily have a perturbative expansion I was talking about, so it doesn't fit with this classification. So I want the differential, but no zeros. And possibly poles. And it is the mathematical result that if you want a differential, globally defined meromorphic differential on the surface with no zeros, but possible poles, these are the only 3 possibilities. So number of zeros minus number of poles is the 2g minus 2. And so in this case, for example, the pole, there are 2 poles. The order of 2 poles at infinity. In this case, the order of 1 pole at 2 points. So in this case, that number is 2, for example. And in this case, the number is 0, for example. And that number go to minus 2, minus 4, etc. You go to higher genus Riemann surface. So you can convince yourself that this is the only possibility. And that matches nicely with the classical R matrix, for example. Now, okay, so maybe I should really finish. But the dream field theorem itself says more. For example, you cannot really find the solution to well, other than AN case in the elliptic cases, for example. And there is a counterpart of that here, that the bundle module has parameter, etc. But anyway, so this is one small thing. And but we are working on other aspects, and hopefully we could explain various results in the integral models from this 4-dimensional gauge theory approach.